All right. Well, thank you everyone for joining today. This is another session of our Lunch Talk series with the MIT Club of Switzerland. And my name is Stella Schiefer, and I'm the current club president. And I'm happy to host today a very exciting guest, Jean-Louis, the CEO of Neocarbons, a very innovative Swiss startup with the technology to capture CO2 and actually turn it into really valuable other products. Jean-Louis received his engineering degrees in chemical engineering from NNSCP Paris and MIT, and completed his MBA at INSEAD afterwards. He has more than 25 years of experience in developing and growing technology-based companies. He started his career as a process and production engineer originally, and has since been working in business development and a variety of management roles, from startups to very large corporates. He will now take the next 20 to 25 minutes or so to walk you through what he's doing, his startup, the technology behind it, and then we'll go into an interactive Q&A session where we'll be able to answer all of your questions. And as I mentioned already, you can open the link we posted here, polf.com/banana147, and post any questions that you come up with during the talk and after. You can also upvote and downvote other people's questions to make sure the questions get asked that people are really interested in. All right, so with no further ado, I want to hand it over to Jean-Louis. Thank you for making it today, and we're excited to hear what you have to say.
Thank you, Stella. Let me check if you see my presentation on the screen. Do you see it? Hello?
I see it. It's just not automatically big. So it's sorry. Do other people see it big, or do you need to? People need to pin it on the screen? Can someone just make a quick comment?
I also see it small, but if it's easy to hit the pin button and make it full screen.
Do people see the little pin button to just pin it themselves?
Okay. So since we have solved the technical issues, good afternoon or good morning. So I'm Jean-Louis. I'm the CEO of Neocarbons, and I would like to thank MIT for hosting me today, and to give a big thank to all of you for risking hypoglycemia. First of all, as you already spotted, just excuse my French, I will try to control the thickness of my accent to make today's journey less painful for your ears. It will be my pleasure to share with you a few thoughts concerning photosynthesis and its potential when industrialized as a contributing technology to tackling major anthropological issues. In the process, I hope to kill some misconceptions about microalgae. So this intervention has been designed as a story taking you through our thought process since 2010, as we moved from a ha-ha towards an industrial equipment and possibly successful business. Thanks, Stella, for the kind introduction. I'd like to put some light on the most important dates of this journey, dates which changed my life. So it all started 1955, I cannot hide that. And until 1977, nothing extraordinary to tell, until late Professor André Strauss of Chimie Paris gave me a great kick to join MIT. So I would like to thank Professor Strauss. And let's not forget these. These are major dates in the journal as well. Okay. I don't know if you remember 2010, there were already lots of talking about global warming and the GHGs. And I saw that picture on the internet and asked myself, is this a premonition? Is this what the Earth is going to be? Even though beautiful, I did not wish this to be a future for us, and especially for my kids. And I started asking myself, can I do something about it? Yes, then don't worry. I must confess that by 2010, I had a strong motivation to look at the issue and see how to contribute to a solution. The first thing to do was an inventory to quantify the phenomenon and to assess the dimension of the efforts to warrant in the future. And NASA helped.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the northern hemisphere, we see the highest concentrations are focused around major emission sources over North America.
It should say Europe and Asia, but I did cut the video too short. And what's worrying, in addition, whether you're a CO2 skeptic or not, is the fact that a lot of countries are now joining us in our standards of living, and what will happen to CO2 when an additional 2.5 million people will start having the same standards of living. So at that time, CO2 was exclusively considered as a poisonous compound. Point. The buzzword was zero emission. Okay, zero emission, it's a fantasy. Zero emissions means death. Okay, this is the moon, it has zero emissions. So we rather preferred the concept of zero net emissions, which we introduced in 2010, because it was also more accessible and techy. You know, it was suited to our engineers' minds searching for a purpose. In addition, it was a great incentive to treat the effluent gases. Okay, whereas zero emissions led to regulating mechanisms based on financial measures and incentives, not to go beyond set thresholds. This approach created an opportunity for traders, not for the planet, as we know by now. Others were promoting less polluting processes, fine, but no one was looking at the issue of CO2 in a holistic way. So we started looking at that. We dug in the fossils mantra and the associated CO2 issue to see what was on the slab, you know. So that's the ugly side of CO2, you know, it's fossils and then boom. The next question is, where do the fossils come from? And then we started seeing something that was very interesting. Fossils come from CO2. Okay, so CO2 is like Janus, has two sides. The conclusion is that whether for foods, feeds, or chemicals, all carbon chains come from CO2. This sounds like, okay, so what? But the consequences are major. First, climate change fight is currently essentially about recycling excess atmospheric CO2, not limiting emissions, but it's not, of course, exclusive from limiting emissions. Second, what if we consider CO2 as the primary resource for our lives and lifestyles, instead of looking at it as a major culprit? This simple sentence can change a lot in people's lives, globally or personally. It did for us, because recycling CO2 can contribute to solve three major anthropogenic issues created by us, the boomers, which otherwise our kids would have to solve. Protein independence, this is a major EU concern, fossil substitution in the chemical industries, and global warming. So by then, our engineer souls looking for a purpose had found a bone to start grinding on. The first question that we had to face was, how much is available? Is this really a vital? Since life began on Earth, we have almost tripled the concentration of CO2 in the atmosphere. This means that we have 1,500 billion tons of excess atmospheric CO2, and this is equivalent to 100 years equivalent of current emissions. Okay. So It's quite untapped resource, and it's free, more or less. The next question that we had is, what are the available technologies to recycle all this CO2? Which ones are the most promising? And is there room to contribute with our knowledge and experience? Very popular in 2010 and since were storage, which is costly but efficacious, fermentation, which was the biggest lure to biofuels, ask solazine or fermental, the one belly up, carbonation, including Medusa oil's solution to stabilize construction sites, electroreduction at Berkeley, which is essentially providing alcohols to the industry, and photosynthesis. These were the 5 technologies that were available. So we looked at those, and we looked at what the guy from NASA just said, you know, that the most efficient natural CO2 sinks are trees and oceans. If it's natural, it's important to know because nature operates at room temperature and normal pressure, and these are big cost issues in most of chemical industries. Okay. So what's happening there? On the surface, it's the trees, photosynthesis. In the oceans, it's again the photosynthesis of phytoplankton. And then we read that article, the oceans are absorbing more carbon than previously thought, which is at the same time good and bad. So anyway, we concluded that photosynthesis was the fastest, the cheapest, and the most efficient CO2 sink and transformation tool that was offered by nature. The bone started to be very tasty. So we decided to focus on industrializing photosynthesis process by mimicking nature and finding a way to farm microalgae industrially. Now, let's look at the constraints of industrialization. And first, okay, a short recall on what photosynthesis is all about, just in case you have forgotten since you were at MIT. So it's essentially you have phototropic organisms like plants or plankton, and they capture carbon, they suck water and minerals. Thanks to the energy of the sun, they transform these into sugars inside the plant, and when the plant metabolizes some of the sugar, it has stored oxygen. Okay. So it's the most important biological process on Earth. It's very effective. It costs a lot of energy, 6 kilowatt-hour per kilogram CO2 transformed, and it has a lousy yield on the energy. And that's good news, I mean, for us, you know. The bone turned into a big feast. We had identified a valuable project by that time. So which were the constraints if we wanted to make a photosynthesis industrial? First, it's energy and energy transfer. You know, 6 kilowatt-hour per kilogram of CO2, when you want to move it from a low enthalpy to a high enthalpy like sugar or alcohol, it's like pushing an Audi 6 at full speed during 2 minutes. I don't know if you tried, but it's quite a lot of energy. It's huge and it has a major impact. So we quickly understood that if we want to industrialize the process, we have to optimize the energy transfer in order to obtain very high productivities per square foot. Energy represents about 85% of variable recycling cost. Whatever the solution you choose for moving CO2 from its level to alcohol or sugars, energy is the major cost factor. And then the whole process would be profitable if we find a way to provide all the energy that's needed per unit volume, but only the energy that's needed, and that's essentially blue and red wavelength, which phototropic organisms absorb, and this is why they are green. So we looked at the traditional photosynthesis technologies, which are powered by the sun. Unfortunately, direct sunlight is not powerful enough to be the energy source for industrializing photosynthesis. That's why current techs like ponds, bags, tubes, etc., they are very costly. They are not suited for remediation of large quantities of CO2. They gave a bad reputation to quote-unquote photobioreactors, and they are costly and inefficient. The good news is this just gave us our target, where we could really contribute with our knowledge and experience. We are happy. I don't know about you, but one major lesson learned from MIT is if thermodynamics don't work against it, there must be a way to do it. Look at it from a different angle. And that was a very crucial lesson for us. So designing a spec sheet for an equipment that would solve the issue was quite easily done. Industrial, real-time, competitive, profitable, and in line with the SDGs. And designing a high productivity energy transfer reactor came naturally as soon as we applied another MIT lesson, designed for the demand and not from the supply. So this is a 3D of our patented reactor. Our calcs, they show that on 5 square meter footprint, a standard 11 cubic meter enclosed industrial reactor is as productive as 1 hectare of alternative sun-powered technologies. Okay, so this 1 hectare of this can be can produce as much as this does on 5 square meter. Okay. In addition, the reactor is scalable ad infinitum because our concept or patented concept is energy per unit volume and not per unit surface. And the production is independent of geographic location as long as you have electricity and water. So you can use it in very remote places to recycle CO2 and produce food and feeds, for example, for fisheries. The second constraint about industrializing photosynthesis or any other process transforming CO2 into high value and high energy compounds is the availability of electricity. It's a huge question because you see this is the cement factory of Lafarge-Holcim near Lausanne. It's a 1 million ton cement factory. So it's also a 1 million ton CO2 emitter. Okay. And that means at 6 kilowatt hour per kilogram, you need 2 gigawatt to fully recycle the CO2 from this plant only. So that's about 1 or 2 nuclear trenches. It's quite a lot. Okay. And then the question is, oh my, can we do that? Yes, well, there is sufficient renewable energy available to cover the world consumption. Recycling CO2 will create a huge demand for the collection and transformation of solar energy, whatever its form, whether it's photovoltaic, wind, or hydropower. Okay, so that's a good hint for your next investments. The third constraint included in our original specs is financial. Will it be competitive and profitable? And the good news are that our simulations show that the investment for an industrial facility is about 10 cents of euro per kilogram CO2 treated. The OPEX is about 50 cents per kilogram of biomass produced and CO2 treated. And the real ROI is attractive, depending, of course, on the end products that the microalgae produce and the microalgae properties. As a note, this is not a competitive route if biofuels are the primary product. Don't try that, you will lose your time and your money. The fourth constraint, supposing you have a technology that takes the load and is profitable to operate, are the markets. Which product can be manufactured that have a high demand for a large existing market? We will see later why large is important. Okay. So the markets for biomass and biomass extracts are two. The first one is the entrance for chemical industries. The second one are the food feeds markets. Now, mass is a core issue because 1 million tons CO2 leads to about 500,000 tons of biomass or 300,000 tons of oil substitutes from a mass balance point of view, simply, okay? And so you need to find huge markets. Just for one cement factory, you need to find huge markets. So the food and feeds market is the market that exhibits the highest traction currently. This is a market for proof of concept, but it is not large enough for large-scale recycling. However, it's a very good go-to-market industry. And you have large corporations, transformers, even consumers looking for alternatives to animal proteins. This is a spirulina, and this is astaxanthin. If you don't know, it's the protein that you give to salmon in fisheries so that the meat is pink. And these are other protein extracts from microalgae. Okay. So if you look at chemical entrants, if you look at microalgae extracts, 1 million tons of CO2 per year leads to 300,000 tons of olefins. So it's quite disruptive in terms of existing markets. And it could disrupt the entire value chain based on fossils. Fortunately, we have two drivers, which are the carbon tax, which is probably going to be around 120 euros per ton. And we have the end consumers. They are a major driver of change. They are starting to look at CO2 recycled products. And this will play a role on the decision of corporate. Okay. One additional good news, if you look at the photosynthesis, is that the products that you will produce, if you are looking for extracts and olefins, they will be such that downstream processing will require no major revamps, which is favorable, of course. You don't need to build new industries. You can maybe add a section in the front and use the existing capabilities or capacities. So the conclusion is that recycling CO2 on an industrial scale with photosynthesis means we can substitute fossils in many chemical industries. If we can't do that, it won't flare. And here the word many is very important. Why? Because it confirms that biomass, because of its versatility, there are about 3,000 strains of natural microalgae, each producing a different protein or fat or lipid. So they are very, very much appropriate for deserving many markets from a single source of raw material, just like the petrochemical industry does today. And the biofuels are for the biofoods. The other lesson that we learned on the way is that if you want to recycle large quantities of CO2 targeted to the chemical industry, you have to form a consortium of best-in-class partners between the guys who pollute, some technologies like ours, but others, electricity providers, engineering groups, and large and diversified downstream customers. If you don't have that customer or that consortium set up, you won't have the capacity of recycling larger CO2 quantities. But the good news is that if they tackle the issue, the industries will transform an upcoming liability, the carbon tax, into profits, and they will have a lot to say about their corporate image and corporate social responsibility. One of the most vivid signs of the CO2 value, is the CO2 value worldwide network. Here we have Europe, we are a member of that. And in this, you have partners like Total, Exxon, Lonza, and many more who are kind of venting a lot of CO2. Okay. So, you know, the 19th century was the century of coal. The 20th century was the century of fossils. And we believe that the 21st century will see the fifth industrial revolution as CO2 goes through biomass and other technologies, and they will become a major resource for our carbon-based society, which won't change. To sum up, you know, if you want to industrialize photosynthesis, you have technologies, they are competitive and profitable, you have traction from the markets, you have financially attractive investments, you got the CEOs here because of CSR and the fact that they can turn a liability into a profit. You must build a consortia. It has a great potential to develop the demand for green energies, and there is an ample supply of free raw material. Isn't that great? So help the planet and start having a daily spoon of global warming. Now, before, if I may, I would like to use an additional 2 minutes of your tap just to give us, our startup Neocarbons, a tap on the back. We are very happy because we have a seal of excellence from the EU. We were recognized by Solar Impulse Foundation as one of the 1,000 technologies worldwide that will have an impact on climate change. We were just selected by Buisson as one of the 31 startups to invest in 2021 in Switzerland. We were successfully incubated by Mass-Challen in Lausanne, and we belong to two of the most important organizations, CO2 Value Europe and the European Algae Biomass Association. We were funded by InnoSuisse, the canton of Vaud within Vaud, and the Foundation for Technological Innovation. That's about 600K plus our savings. Where do we stand? We have built a prototype which we have tested at the University of Zurich in Wädenswil, and the objective was to prove on 5 strains of algae, the major strains, that our patent was valid, and we did that. And now we are in the next phase, which is starting this month, end of this month. We shall prove the economics of our design in a semi-industrial pilot reactor, 50 liter. Our roadmap is quite straightforward. 20 and 2021, we are focusing on the prototype and the semi-industrial pilot tests. In 22, we will build a 1 cubic meter industrial on-site testing facility. And in 23, we will start selling equipment or products. That is still, the jury is still out on that, but probably both. So our next fundraising is going to be about 2.5 million in tranches, starting with a 500K in 2021, Q2 2021, which will be used to hire staff, build up business development and R&D structure. Our preferred form, of course, is an interest-bearing, is non-dilutive, interest-bearing convertible debt. If you can't do otherwise, equity. Preferred investors are angels and not non-industry savvy venture capital. And we are also applying for development funds from the EU, especially the Green Deal and the protein independence arms of the EU policy. Last but not least, we have a great team of contributors from R&D to the markets with Fabrice Guény, ex-CEO of Cian, the leading supplier of clothing in Europe, We have a great technology support from Helbling and from our contractor who is building our prototype. And we have top quality advisors, Isabel from Harvard, Ralph is a major contributor to InnoSwiss, and Daniel was our mentor at the Mass Challenge. So, thank you for your attention. You can reach us via the contact form on our website or directly by email or phone, and we shall be happy to talk with you. Here are our references. Now, Stella, the floor is yours.
Yeah, well, or yours actually, because the question is also to you. But thank you so much for the talk, and we'll open it up to Q&A with all of you now. I'll also just present the questions. We have a few already, and feel free to just add more, of course, as we go through this. We have one question, which I guess is the first one, which is just about the topic itself. Could you just explain again what the difference is between your reactor and the photobioreactors you mentioned before? How do you get light into a volumetrically compact reactor? Can you just explain the technology a little bit again?
Yeah. So how do we get light? This is kind of a trade secret. I have here it's a mock-up of the reactor. So you can imagine on each of the surface is acting like a sun surface. Okay. So we have here on 20 liter, we have about 20 times the power of the sun per cubic liter, per liter. Okay. The major difference is that we provide, with this system, we provide the energy per unit volume. Whereas the reactors that I showed to you, the tubes, the bags, they only get the power of the sun, and they get it per square meter exposure. And as mentioned, the sun gives you 3.5 kilowatt hour per day and per square meter, and you need 6 to recycle 1 kilogram of CO2. So that's what makes us about 300 times more productive per square meter footprint. This design, patented. Are you happy with the answer?
I guess feel free to unmute. I'm not sure who asked the question and comment on that.
Okay.
Maybe generally, like, so you mentioned like a bunch of people who are currently already working with you. Is that the full team? Like, how big is the full team working? Are you actually expanding your team right now?
Okay. So what's the next question, please?
Sorry. I guess it was this. I guess like about the team, and if you are expanding your team at this time.
Yes, that's the next step. As soon as we have the funds, the first tranche of 500K, we will build the industrial 1 cubic meter reactor, and we will hire this year 2 people and next year 4 people, all in business development and in R&D, project management R&D. So you can send us your resume.
So this technology seems to require huge storage spaces for all the microbes. Do you have an estimate of what that would look like if we recycle all excess CO2 in Switzerland?
No, I did not make that computation. Well, in fact, it requires much less footprint than competitive photosynthetic technologies or even fermentation. Because we work in a volume, so you can have a reactor of 3, 5, or 6 meter high. And each time you increase the height of the reactor, you increase the productivity per square meter. In addition, because we can give the energy that is needed per unit volume, we can reach higher concentrations, about 2 or 3 times higher concentration than they reach in the alternative sun-based technologies. So no, we don't need a lot of storage space.
Sorry, Alice. So there's a question about the energy demand. Could you again explain the energy demand to offset the emissions of the cement production in Lausanne, and maybe set it in relation to the monthly energy production of around 5.5 terawatt hours in Switzerland?
Yes, okay. If you want to move CO2 and transform it into high value added compounds like fats, lipids, or alcohol, you have to put about 6 kilowatt hour per kilogram CO2 treated, just to bring the CO2 from a low level of energy to a high level of energy. Okay. So if you have to treat 1 million tons of CO2 per year, it's about 15 kilograms per second, and that means you have to have 2 gigawatt of renewable electricity available. And I can't compare that to the 15 terawatts, but I guess it's a ratio from 10 to the 9 to 10 to the 15th. But it's a lot of energy, and this, whatever route you choose to recycle CO2 and transform it into a high value added product, the thermodynamics tell you you have to put that energy, which is normal after all, because that energy, you got it in the other direction when you burnt the alcohols or the fats, you recovered the energy and you release the CO2. Now, if you want to recycle the process, you have to give back the energy. Fortunately, we know now how to capture renewable energy. If we had not those photovoltaic or windmills, then the process would not be a virtuous process. We would spend much more energy in supplying electricity than we would recover in the final goods.
There's one more question around how does the reactor work with algae? Are they two separate methods of CO2 extraction?
There are many methods for capturing and or transforming the CO2. We saw them. The first one is you just dig a hole and you compress, liquefy, and chill CO2 and store it in the ground. The other one is fermentation, but that's a lure because fermentation uses biomass and sugars as feeds and also releases CO2. The other ones were carbonatation, you make bricks, okay? Or what Medusa oil is doing is great. It's they capture the CO2 and they carbonate it in the ground so they can solidify construction sites without having to use a lot of very expensive machines on the construction site. And the last one before photosynthesis is electroreduction, where you pass the CO2 over a catalyst, metallic catalyst. You inject electricity, the same amount as we do probably, and then you get alcohols at the exit of the plant. And it was Opus 12 at that time, operating in Berkeley. I don't know where they are now, but the subject is quite interesting. And yeah, those are the 5 methods. We chose photosynthesis because it operates at room temperature, it's normal pressure, and it's extremely versatile.
Okay. What percentage of CO2 that you recycle with your system is required to produce the energy to run the reactor? Even renewable electricity has some associated carbon emissions built in.
Yes, I agree with that. I don't know the percentage, but it's If you use photovoltaic panels, you have about 58 grams, no, 13 grams of CO2 per kilowatt-hour. So you have about 30 grams of CO2 per kilogram of CO2 captured. But, you know, there is no perfect solution for that. I've heard lots of buts with 1 and 2 T's, but there is a cost associated with the recycling of CO2, and that cost is this renewable electricity, their CO2 impact, which is going to go down because as we move forward and as we have more and more renewable electricity to produce the windmills and all these, then their own impact on CO2 will diminish as well. You have to look at the thing, you know, with a long-term perspective. It's going to go down on the long term. Today, it's a little bit higher, but it's still very profitable in terms of finance, naturally, and in terms of CO2 mass balance.
Could this technology also be applied to produce fuels to complete a zero-emission cycle? So I guess with microalgae, I guess it's a question, would microalgae also be able to serve as fuels?
Yes, but I would not recommend it. Just because if you look at the prices on the market, the fuels are the lowest priced commodity. And if you want to start a new technology, you start with high-paying markets. Yes, you can produce fuels, or you can burn the biomass, the envelope of the algae. Once you have extracted the products that are of interest to you, whether it's proteins or lipids or whatever they produce, then you're left with the envelope, and that envelope is about 20% of the total mass, and you can dry it and burn it, and you recover the energy that is in the envelope. So it's a form of fuel. I would not go personally. I would not go for the biofuel market as a first market.
So this tech, another question. This tech relies on the fact that societies keep producing excess CO2. But with the rise of renewable energy and global efforts against climate change, the source CO2 will go down at some point. What would be the solution then?
Well, as mentioned, we have about 100 years of free CO2 resource in excess in the atmosphere. And if we want to tackle climate change, we have, of course, to limit emissions, but we have to tackle that excess CO2, 1,500 billion tons. So, yeah, maybe at some point, I don't think that we will end up producing no CO2. Simple reason. For example, you recycle CO2, you make plastics. Okay, what do you do with the plastics? You burn them and you get some more CO2. And what fuels the whole process is the renewable energy from the sun. So the real worry is not the supply of CO2. The real worry is the sun. Is it going to keep giving us free energy for long enough?
Yeah, there's definitely still a lot of carbon around for a while. Oh, I think we had this one. Another question: how far is Neocarbon in its R&D? Is the tech already mature enough to produce proteins at a large scale? I guess I go to the question how you are in terms of timeline.
As mentioned, we are starting the semi-industrial pilot test with the University of Zurich this month. That will be in a 50-liter reactor. The 1 cubic meter reactor will be probably in 2022. So the tech is mature, but it is not yet mature enough to produce at a large scale. We have produced Microalgae, we have produced extracts at the university, but these were for the test that we did for the prototype and now the pilot. That will come in 1 year. End of 2022, we will be capable of producing at large scale, whatever it means. Large scale, if you talk to a guy in the academy, 20 liters is already large scale. If you talk to me, a production engineer of some chemicals, a large scale is 100,000 tons a year. Minimum.
All right. Just about your journey. So what has been the biggest challenge of the project along the way for you?
Keeping the spirits in spite of all the winds that were blowing in other directions. So when we started, the whole investment community was focused on biofuels and fermentation, and all the money went there. So we didn't have an ear to our solution. And also, when we started, microalgae had a very bad reputation because of the technology that was used to farm them, and which was not cost-effective and not efficient. So we had to fight against all this. And about 2 years ago, when people started realizing that fermentation was a big flop, they started looking at other possibilities, especially the people in the food and feeds market. And this is where we got traction. So the biggest challenge is not technical. The biggest challenge comes from the environment.
Okay. Then someone's asking how many this reactors of this equipment needs. Sorry, I'm not sure I understand the question. How many this equipment needs in the earth to absorb current excess levels of CO2? Okay, I guess how many reactors would it need to absorb all the current excess level of CO2?
It depends on your time frame. One reactor can process about 165 tons of CO2 per year. Okay, over 5 square meters for a standard 11 cubic meter reactor. So these are the three numbers that you need to compute the answer to that. And in addition, if you have very fast microalgae, like there is lots of research going on right now to improve the efficiency of the microalgae. And so the ones we have to date are okay, but kind of slow. If you have a very fast microalgae, you can recycle much more CO2 per square meter in our reactor, provided you have the energy and the water. And also, if I can add something, it's not the only solution. There will be other solutions. There will be storage. Total is very involved into storage. There will be electro reduction. At some point in time, electro reduction will be industrial and will provide large quantities of alcohols to the ISF and other companies. And we, with our technology, we will focus on more niche products with a high value added.
We don't have any questions here right now. Let me maybe just ask one question, which we can use as a wrap up. I guess from the people joining this call or anyone who's interested in this technology, kind of what's the best way to support the company? What type of kind of input or feedback or support are you looking for that any one of us may be having or may be able to provide the company? In terms of questions or financing or what are things that we can actually support this initiative?
So you can send resumes of the best people around that you know. You can help us also with being a side partner to test the technology. These are two important things that we need for the time being. And of course, you can spread the word.
All right. If there are no instant questions, we will also be sharing the recording of this talk later on, and we will also be able to share the slides later so that you can go through it in more detail. If you have questions, I think you're great that you'll be available to take questions over email at a later point as well. So feel free to reach out. And otherwise, we'll officially close it now. But for anyone still interested or still have questions, please feel free to stick around. I just see that one more question that came up.
Okay.
Is there a reason we're not using directly sunlight in your reactor?
Yes, as mentioned, sunlight is not powerful enough. So we go away from sunlight. It just doesn't have the power. And it would be very expensive to have a collector on top of a reactor to just capture 3.5 kilowatt hour per square meter per day when you inject about 100 kilowatts in a reactor. It doesn't make sense to us. The sun is not the solution if you want to industrialize photosynthesis. And this is why we have a project. If the sun were a solution, we would not have a project.
Okay. Yeah, I guess if you have any more questions, feel free to stick around. Otherwise, I'll just officially close the talk for today. Thank you, everyone, for joining. And thank you so much for presenting and sharing with us your vision for Neocarbons. I'll be really grateful to have you. Thank you.
Thank you, Stella.